Hello everyone. We will solve the 9 questions today from June 2020 CSIR-NET question paper. Okay, we are doing only the organic questions. So let's start with the question 11. The question 11 says the natural product that gives a signal at 218 ppm, delta 218 ppm in its carbon 13 NMR spectrum is. So now you have to just know the structure to know this. The only thing you have to know is in carbon 13 NMR, ketones peak come around 205 to 220 and aldehyde come around 190 to 200. What they have asked is 218. So we almost know that it must be ketone. Okay. Acids and ester comes from 160 to 185. Aromatic region comes around 125 to 150 and alkenes come around 115 to 140. Right. So now let us look at the molecules. Alpha pinene. So alpha pinene, somehow to remember this ene is there, so it's alkene, okay, and it's a bicyclic system. So this will definitely not have, and this will not show peak at 218. Camphor looks very good to me because it is a ketone bicyclic system. Let us look at geraniol. So geraniol nothing has doesn't have anything which is which will have something about 200. This one is again a ketone, carbon. But carbon, I don't know how you remember structure, but if you remember structure, this is what. But never ever take risks in these questions. If you don't know the structure, you will be completely wrong. Okay, and it's tough to remember so many natural product structure. But carbon has basically alpha beta unsaturated ketone. So if you have alpha beta unsaturated ketone, you know conjugation occurs. So when conjugation occurs, you will have another canonical structure. You know that the canonical structure double bond comes here. You get a C single bond O minus. So this single bond O has lot of single bond character. So bond is weaker, and therefore NMR will C13 NMR will come at lower frequency. It will not come at 218. Okay. So yeah, it should be lowering of frequency. So very clearly your answer is camphor, option number B. Okay. Next question. The correct order of stability for the carbocation A to C. So we are having this. So you are having vinylic carbocation, you are having a simple carbocation, and you are having allylic carbocation. Now we have to understand the order of stability. So first thing to understand is why is it unstable? It is unstable because of positive charge. The more localized positive charge is, the more it is staying in one place, more unstable it is, because if it is spread around, then what happens? Each of them will have less amount of positive charge. This positive charge is the main problem. Now here what happens when you are having allylic, this pi bond conjugates. Basically there is a p orbital here, there is a p orbital here, and there is a p orbital here. These two p orbitals have 1 electron, and this p orbital is vacant. So they say, why you are vacant? You are also a brother. So let us just join hand to hand. So when it joins hand to hand, what happens? The positive charge is shared away, the electron deficiency is shared away between these three p orbitals. So if I draw the canonical structure, how do I get? I get canonical structure something like this. Okay. Yeah. So that means each carbon is having just half positive charge. So it is much delocalized. So allylic will be more stable, no doubt about it. So C should be highest. So very clearly answer can be either C or D or A. It cannot be B or C. Okay. Now we have to look at between A and C. Sorry, A and B. Now this carbon, if you forget the positive charge, this carbon initially was sp3 hybridized. Now it gets carbocation, so it becomes sp2 hybridized. Correct? Whereas here it was initially sp2 hybridized. Once carbocation is formed, it becomes sp hybridized. So this, the molecule A has more S character, molecule B has lesser S character. Correct? Because if you look from sp2 and sp3 also, sp2 has more S character, because 3 orbitals are there. Out of 3 one is having one out of 3 1 is S, so 1/3 is S character, whereas here out of 4 1 is S, so 1/4 is S character. So very clearly this one has more S character. So when something has more S character, when something has more s character, it is more electronegative. Please understand, s orbital is spherical, closer towards nucleus, more penetrative power than your p orbital, and therefore it is more electronegative. Electronegative means what? It needs electron, but what are you giving? You are giving it electron deficiency. So this is definitely least stable. B will be more stable. So answer will be option number D. C more stable, then comes B, then comes A. Okay, so whatever I said I have written here, you can go through it slowly. Okay, next question. The stereochemical relation between HA and HB in this molecule is A anisotropic, B homotropic, diastereotropic, constitutional, heterotropic. So we did this in the previous question paper. Okay, so I will not discuss so much about it. We very clearly discussed about anisotropic and diastereotropic. You can look into the my CSIR previous question paper. Just I will explain what is homotropic. Homotropic also I had explained. Constitutional heterotropic is just two different hydrogens which are not at all chemically similar. So in an anisotropic, what we should do is we should change HA and HB, put some other substituent, and then see that when the two substituents are coming, are they a pair of enantiomers? Okay, maybe I'll just do it a little more. So let me take this opportunity, let me explain whole thing so that this question is complete in itself. So let's start with homotropic. So I would give you a good example. Something like this is there. So HA and HB, imagine I break HA and put Br here, and then I break HB and put Br here. Now if you look at it, both of them are same, it is not chiral, so they are not even mirror images, they are exactly superimposable on each other. So when two hydrogens are there like that, that if you exchange them, you still get same, they are called as homotropic. So of course they will be absolutely same, so they will not show any difference anywhere, neither in NMR nor in your polarimeter, right? Anisotropic, what happens? Initially it is not chiral, it is pro-chiral. But if I change HA and HB, instead of HA if I put Br, instead of HB I put Br, now this is chiral. So now you can look that these two are mirror images, and they are non-superimposable on each other, right? So when they are non-superimposable mirror image, they are enantiomer. So this HA and HB are anisotropic in nature. Again you have to remember, because they are enantiotropic, enantiomers do not show difference in NMR. So proton and NMR, still both of them will show us two proton peak, a single peak. It will not show two different peaks. HA and HB will not show different. When we come to diastereotropic, what happens is something like this. Already a chiral center is there, and I want to know HA and HB, what happens. So if I put instead of HA Br and instead of HB I put Br, then what happens? These two parties mirror image, yes, and these two parties superimposable on each other. So that means overall what happens, 5 and 6 overall, they are neither mirror image nor they are superimposable on each other. So what happens? They are diastereomers. Enantiomers, we know enantiomers are stereoisomers which are non-superimposable mirror images, whereas diastereomers are stereoisomers which are non-superimposable non-mirror images. Okay, so diastereomers, you know, they show difference. NMR, they show different peaks. So very clearly, if you see NMR, HA and HB will show two different peaks. Each of them will show one hydrogen peak and a different chemical shift, because they are diastereomic in nature. So this diastereotropic is very important for this purpose. Okay. Heterotropic groups are just something like this. Okay, HA and HB, they are very different because HB is closer to C and HA is different. So even if we change, doesn't matter anything. Okay. Now let us look at the given question. Now initially this was very interesting question. Okay, initially this question there is no chirality, because we think about what is called atropisomerism. So because these substances are bulky, this ring does not have freedom to rotate. Okay, so what happens? So if you have, imagine X substituent here and you have Y substituent here. So if some of them are staying like up, so X is up above the screen and Y is below the screen, and then you have another molecule, in that you can put X below the screen and Y above the screen. Then it becomes what is called as uh, it shows attrop isomerism. They will be enantiomers, they will be mirror images which are not superimposable. But here such issue was not there. Why? Because these both were ethyl group, these both are ethyl group. So what we think is, initially because it is achiral, initially it is achiral, so if we change A and B, now this we can see very clearly, this carbon is prochiral. If we change HA and we put Br here, and we change HB and put Br here, this carbon becomes chiral carbon. Okay, so we'll think that, okay, so these two hydrogens are anisotropic in nature. But very interestingly, it is not anisotropic, it is diastereotropic. Why? Because once you change it to Br or Br and then H is there, then this substituent is different and this substituent is different, correct? So now some of them will be above the plane, in some other, some of this ethyl will be above the plane. So what happens then? They become, they show attrop isomerism, they show enantiomeric effect hereafter, and then because HA and HB are anisotropic in nature, they become diastereotropic. Because for diastereotropic we explained that we need beforehand, we need one chiral center beforehand. So similarly here also it is same thing. So that's why these two are there, and therefore this will be diastereotropic in nature. I have written this in great detail, please go through it slowly. Maybe you can go from the beginning slowly, okay? Wherever you you feel you are not able to read, please pause it and then read it. Very important topic, please understand and then only move ahead. Moving to the next question, question number 14. It says the total bond order of adjacent carbon atoms of benzene. Now you cannot get a simpler question, you can very clearly see there are two canonical structures. So canonical structure, what it means is not that Sunday these two carbon will have double bond, on Monday these two carbon will become single bond, not even for a second or microsecond or femtosecond, whatever you think. The real structure is somewhere hybridized between them. So that means this has equal amount of double bond character and equal amount of single bond character. So it will be between average of them. So 2 double bond average of 2 plus 1, right? 2 plus 1. So that is 3. So average becomes 1.5. Okay, average becomes 1.5, and actually it is little less than 1.5. It's 1.4, because there are some other structures also, resonance structures, which we do not show generally for benzene. Some Dewar structures are there. Okay. Next question, question number 15. A compound that exhibits the following spectral data: IR 1740 per centimeter. Now, what is 1740? 1740, generally 1735 is for esters. Okay, so 1740 will also be esters, little more some electronegative group will be there. That's all you can make out. And proton NMR, it says there is triplet at 0.9. 0.9 means highly shielded, and triplet in 3 proton, that means CH3 is there clearly. Triplet means besides CH2. Then you are having 1.6 sextet 2 proton signal. 2 proton signal means CH2, it has to be CH2, and it must be beside some 5 hydrogen atoms. So must be beside something like I can think of is CH3 and CH2, something like this. That's what should show sextet, unless they are diisotopic in nature. Okay. So if you look here, so this CH2 is 2 proton peak, and then 3 plus 2 5 are there. So 5 plus 1 6, and this should show sextet. Okay. And then what else you are having? Then you are having 2.3 triplet 2 hydrogen. So again you are having CH2 beside CH3 or something like that, because then it is triplet. And 4.6 doublet 2 hydrogen. So 2 hydrogens are there, and it is beside some CH. Then you are having 5.2 doublet 1 proton. So there is some CH which is beside another CH. Then 5.4, it is doublet 1 hydrogen. So again same CH is there beside another CH. So these two should be neighbor in all probabilities, 5.2 and 5.4, right? And then you are having 5.9 multiplet 1 proton, 5.9 multiplet 1 proton. So it is 1 proton is there, beside it so many hydrogens are there. So let us look at the molecule. So A, B, C and D, all of them are esters. But if you look B, what happens? B is an ester, and beside carbonyl group you are having this unsaturation, alpha beta unsaturation kind of stuff. So this moves here. So what happens? C double bond O bond becomes weak. So it gets a single bond character. So therefore it will not remain at 135, it should reduce, it will not remain at 1735, it should reduce less than 1735, but here value is 1740. So very clearly you can remove off B. Okay. Now let us look at other molecules. In A you are having 1 CH3, right? In C also you are having 1 CH3, but in D you are having 2 CH3s. But here uh, here they have given only one molecule is there where which is having CH3, only one CH3 is there, because you can see 3 protons, only one is there, no other signal is there with 3 protons. Very clearly we can neglect of D. Okay. And also if you look at 71, so peak 100%, so it is a stable peak. When with this also we can know either it is A or C. So what happens is something like this occurs. So in esters generally what happens, first you ionize it, you get a radical, and this bond was not done properly, this should come here like that, and this breaks up, right? It breaks up, so you get triple bond like that. Now this corresponds to 71. So what is there? 71 oxygen, carbon, CH2, CH2, CH3. Now if we look here between A and C, so A has the CH3, CH2, C triple bond O, but here it is CH2, CH2, it has 2 hydrogens less. So it should have come at 69 and not 71. So very clearly we have answer as A. But in examination I would have just marked A and moved ahead because this is very clear, but right now I will take this opportunity to explain this NMR, behind NMR spectroscopy through it. Okay, it's an interesting question. Okay, so now what happens is, this is the molecule. Let us understand how these peaks will come. So this is very clear, no problem about it, because it is CH3, very highly shielded, because there is no electronegative group beside it. So this should show around that the first CH3, and this will come as what? This will come as triplet, because 2 hydrogens are beside it. So 3 proton peak triplet. So this is the one. This is done. This part is done. Okay. Let us look at something else. Now this is the one. Now let us look at this CH2. So now CH2 has 2 hydrogens, right? And beside this you are having another 2 hydrogens, right? And then you are having 3 hydrogens here, because it is CH3, right? So 3 plus 2 5. So these two hydrogens should show as sextet. So 2 hydrogen signal as sextet. So let us look. So 1.6, this is the one. So this also is done. So till now which all we have done of? Whichever we are doing, we will keep marking them. So we have done 1 and we have done 2, right? Then what will this one will show up? See here, now this is quite decelerated because it is next to CO. So this proton, this electron density from this will come, can pump into the anti-bonding orbital of C double bond, okay, pi bond, anti-bonding pi orbital. So now what happens here, this CH2 is beside another CH2, so it should show 2 proton peak as triplet because this does not have any hydrogen. So 2 proton peak triplet 2.3, quite high. So this is also done. So this is also done. This is also done. Now let us look here. So here it has two hydrogens, and there is a hydrogen here, and there is a hydrogen here. So these two hydrogens are actually identical, okay. So this should show 2 proton peak and only one hydrogen is there, so it should show as doublet. Even these hydrogens are there, you can say that yeah, why not coupling about this, but generally these are too far. 4 proton signal, this is like 1 2 3 4 and the 2th allylic, the coupling is very little, almost 0. So this will not couple, but this will couple with this, and so these two hydrogens will show us triplet, and that's what is seen, and therefore this is also done. Yes, 4.6, see this is beside oxygen, highly deshielded, okay. So this is your fourth. So two hydrogens are there, and it comes as doublet. Now what about this one? So this is beside this hydrogen, okay, this is beside this hydrogen. Now this should come as, because just now we saw that these two hydrogens were split by this hydrogen, right? We saw that the CH2 at position 4 was split by this hydrogen. So very clearly this hydrogen will also be split by these two hydrogens. Not only that, this will be split by this trans has quite high coupling constant, and then it will be cis is a little lower, and then with this, so it will appear as multiplet. So this should be the value 5.9 multiplet, 100%, okay. So we can mark this also, this will be your 5, Let us look little bit at the coupling constant. This is important, okay. We should take this opportunity to learn. Yeah, see this cis coupling is around 6 to 4, trans coupling is higher, 11 to 18, but in alkene geminal coupling is very low. It will not be seen most of the times unless it is very high, some 600 megahertz NMR. Apart from this is what I wanted to see, this coupling is around 4 to 10, it's quite low, okay, it's lesser than even cis. So here what we said was right. Let me rub it. Oh, here I was showing right here, yeah. So I was right here. This hydrogen will be first split by trans, so it will come as doublet, and then again split by this hydrogen because this is lower, cis has lower coupling constant, okay. So first as doublet, then doublet of doublet, and then another these two hydrogens, so doublet of doublet, which will be again split into triplet, so that is multiplet, okay. So we have got this, 5 is done, okay. Now what about these two? Please understand, vicinal coupling on alkene, not vicinal, I am so sorry, geminal coupling on alkene is too weak, ultra weak. It will not show up unless you have very high proton NMR resolution, okay. So these two will not even split each other, and therefore you have to do it from something like this, okay. So now what happens is, this will be split by this first, and then very little with this. So if it is not high resolution, it will not show, so it will come as doublet. So that's what it is seen. One of them is this, and this also will be split, Again cis, it will be little less splitting, but it will also come as doublet. So these two are the ones. Therefore, very clearly your answer is option number A. I know I went quite fast. What I'll do is I'll go very slowly. I'll roll down. Please pause it where you don't understand, but please understand this question properly. Okay. Moving on to the next question, question number 16. The structure A in the following reaction is. So this one, there is no other way you have to go by trial and error method. Let's start with option A. First thing is you are putting light photochemical reaction. Very clearly 2 plus 2 addition will happen. You know 2 plus 2 is photochemically allowed according to your FMO approach. So these two will form a ring. Okay. So these two will go and form a 4-membered ring. Second step, what is there? Second step, you are doing ozone lysis followed by dimethyl sulfide. So this is reduction. So it will not it will make aldehyde or ketone. It will not allow it to oxidize to carboxylic acid, and one extra oxygen goes in this dimethyl sulfide and goes out as dimethyl sulfoxide, right? So next step is this cleaves up and you are getting this, and dimethyl sulfoxide is released. So please understand, you have to nothing you have to do, you have to just break this double bond in between and put oxygens on in between both of them. So that's what you are doing. Don't even bother to see this part, ozone is what is happening. Just understand you are breaking here, you know, putting C double bond O here. Okay, here you are putting C double bond O, that's what I have shown here, and you are putting C double bond O here. So that's what I am showing here, C double bond O, right? And then what's the last step? Last step, let me just see. Yeah, you are using sodium methoxide and in ethanol. Ethanol is definitely a solvent and sodium methoxide is a base. So basically it is undergoing aldol condensation. So aldol condensations, you know, it's very easy. You should have CH2 besides C double bond O. So at carbon number 1 I am having CH2 because actually it is CH3, but we'll forget one hydrogen, and so possible, and there is another hydrogen here, and carbon number 3 also has 2 hydrogens. So these two can undergo condensation with the any of the oxygens, but it will not undergo with ester, it will undergo with the ketone. So with this, so H2O should be lost, H2O has to be lost. So if H2O is lost, what happens? If at carbon 3 it occurs, it will be highly strained ring, right? So it will not go from here, rather H2O will be lost from rather H2O is lost from this part. So this part undergoes condensation reaction. Condensation is basically two moieties come and something has to be released here, H2 is being released, and this double bond extends here, and this is what is your structure. You can look here, your structure is, oh sorry, this is what is your structure. You get double bond here. So I must have done the mechanism also. Let us look here. So this H2 and O is lost and you get this structure. This is what is given the question very clearly. Answer is option number A. So mechanism, we know that this is very simple. You first proton is released. This proton is acidic because the conjugate base stabilized over this carbonyl, and then this I should have drawn, yeah. So this double bond comes here, this goes and attacks on this one, this comes up, it takes again proton from the solvent, and then again this is picked up, this proton, this comes here and OH is lost, and you are getting this structure. Okay, so you understand OH minus is very bad leaving group, but it always leaves when alkene is formed because double bond is pushing in the anti-bonding orbital and then this goes away. But if you think some nucleophile go and attack on OH minus leaves, that will not occur, but it always happens if alkene is being formed, right? Thus the answer is your option number A. Question number 17. So you are having this molecule, you are having bromo and OH group, and then they are adding NH2. We need not worry about NS part, but we should worry about this NH2 part, okay. And then you are having dead. So whenever you find question with dead or diad, okay, with dead or diad all in capitals, then please remember it is Mitsunobu Nobu reaction. Very reliable reaction. I have done many times, it never fails, okay. So dead or diad, and then you are having PPSC. So first step very clearly is your Mitsunobu reaction. Let's understand, and then it asks what product is formed. So in Mitsunobu reaction, I have put great details. Let's read every bit of it, okay. So we know what is Mitsunobu reaction. It converts primary or secondary alcohol into esters or ethers or thioethers and many other things, right. But mostly it is used for converting alcohols into esters, right. And the nucleophile employed should be acidic. Very important, the nucleophile should be acidic, since dead or diad must be protonated during course of reaction to prevent from further side reactions, okay. Then nitrogen nucleophiles also are used, something like phthalimide, hydrogen, azide, etc. So generally what happens, it is something like this: alcohol is there and acid is there. You know, acid is low, reactivity is very low, but if you are able to react, H2O will be released and you get ester. So this reaction occurs here. So we will be thinking like something like this must be occurring. Oxygen goes and attacks on this carbon and this OH must be leaving somewhere. But if that happens, then you should get retention of configuration. But in Mitsunobu, that is very important, there is inversion of configuration. Oh, I'm so sorry, here here OH is there, it should have been hydrogen, okay, it should have been hydrogen. And similarly here also it should have been hydrogen and N3 gets. So very important point is it undergoes what is called as inversion of configuration, okay, it undergoes inversion of configuration, right. In the given question, there is alcohol, we saw very clearly, and then you are having NSNH2. NSNH2 is this compound. Now this proton is acidic because if you remove this proton, you get negative charge which gets stabilized over sulfonyl, okay, which gets stabilized over sulfonyl. So this is what is being used. So now question is, and now it becomes very simple. When you look at the question, you will understand. So this part is there, so this part will go will be attacked by NSNH2, we saw that, and here it will form the bond, right. So let's understand the Mitsunobu very clearly. First step is triphenyl phosphine goes and attacks here on the nitrogen, you get negative charge, and this negative charge needs to be stabilized, so it will pick up proton. That's why we needed acidic group. So this amine was acidic, it picks up proton, you get here and you get stabilized like that. And then third step, this oxygen goes and attacks PPS3, because PPS3 can form phosphorus can form 5 bonds. Initially it was 3 bonds, then it formed 4 bonds, became positive charge. There is a vacant d orbital, this goes and attacks and you get this, and then this leaves here, and this oxygen becomes neutral, then it again attack here, this comes out, you get O plus PPS3. Please remember, phosphorus always like to have plus 5 oxygen state rather than plus 3, and then this NH minus which has come out, okay, this NH minus which has come out, oh I'm so sorry, yeah, this is the one which we are attacking. It had lost the proton. Where did it lose the proton? Yeah, this is where it had lost the proton. Proton was picked up. Now this is the species which is going and attacking now. So this NH2 is going and attacking here. See, that's why inversion of configuration occurs, because it attacking on the anti-bonding molecular orbital of this C single bond O. So this goes and attacks here, and you get this is your first product, okay. Next step is addition of cesium carbonate, okay. I should have put this S small letter, and this S also small s, okay. Cesium carbonate and tetrabutyl amine. Now cesium carbonate is a base, very interesting base it is. Generally when you think about carbonate, it's a weak base. Here also it is weak but very powerful, because CCM is very large in size. That means highly electropositive. It doesn't want to keep its electron with itself because nucleus is too much inside and so big in size. So electrons are not happy with CCM, so it pushes away all the electron. So carbonate is highly basic here. Okay, it is much more basic than your sodium carbonate. And apart from that, CCM, it helps to it helps in cyclization reaction. Basically, CCM coordinates with two ends of molecule and bring them together, favoring bimolecular attack. And where is tetrabutyl ammonium iodide? Just one second. Yeah, you are adding tetrabutyl ammonium iodide also. So you know this is basically for adding I minus. So I minus, if I put something like Ki, it will not dissolve. That's why you put as organic salt. Sorry, and I minus. I'm so sorry. Okay, so you are having tetrabutyl ammonium iodide. So this I minus we are adding, which helps in SN2 reactions. Okay. So once this is formed, this tetrabutyl ammonium iodide removes this, becomes iodide, and this carbonate picks up this proton, you get negative charge. Now this carbonate, this CCM helps in coordinating this nitrogen and this iodine, because iodine has lone pair of electron, nitrogen also lost a proton and gets a negative charge. Now so that this reaction becomes intramolecular. CCM carbonate is known for this. Please remember, whenever you see CCM carbonate, please remember it will always make reaction occur in intramolecular, not intermolecular. Otherwise this could have gone and attacked another molecule. Imagine another molecule comes with this iodo and it could have attacked here. Intermolecular is more favorable, like you can see they are quite far, but CCM carbonate makes sure, because it cyclizes them, it coordinates both of them, that it undergoes intramolecular reaction. So this S minus goes and attacks here, this leaves, and you get this kind of ring. The last step is addition of thiophenol and KOH. So thiophenol, you know, is acidic, quite acidic, much more acidic than phenol, and you get pH S minus. And now this goes and attacks here, this comes up, this goes, and this leaves and takes away proton, you get this. The answer is option number D. Okay, quite tough question. I'll go once again slowly. Please go through it carefully, read line by line. Every word is important. Okay. Next question. Among the following, the total number of terpenes or terpenoids is. So terpenoids, we know they are basically polymers of isoprene units. Isoprene is isopentene. So this is isoprene unit, and it has a this is the head part where isopropyl part is there, and this in two carbons are there, that is ethyl part of that is called as tail. Okay, so they either add head to head or head to tail or tail to tail, but generally head to tail is better. So when you have to find out how many terpenes are terpenes or terpenoids are there, just find out how many molecules have number of carbons in multiplets of 5. You can see here 1, 2, 3, 4, 5 are there. So 5. So if you count, I have done all this hard work, you can read through it and you will see that molecule 1, 2, 4, 5, 6, 7, 9 and 10 have this. So the answer is 7. Okay, and this head and tail I have tried to explain. See here 1, 2, 3, this isopropyl, whenever you look, this is definitely head part, and 1, 2, 3, 4, 5, this is tail part. So tail part is being added to this part is again head part, you can see this, and then this breaks up and then you are having this tail part is attached to another head part. That's how it is. Okay, so now you can look once again, you will find out that 7 of them are multiplets of 5. And terpenes are basically carbon and hydrogen. Terpenoids have oxygen in it. Okay, so generally hydroxyl or ketones kind of stuff. Question number 19, last question for this video. It says for the molecule, this molecule, one OH is here, the number of possible stereoisomers. Okay, so there is only one chiral center, we can see very clearly. This is the chiral center because carbon, hydrogen, OH is there, and these are two different groups. So it should lead to only two stereoisomers, correct? But there are two double bonds. So this is double bond and this is double bond. So this will give E and Z, this will also give E and Z. So it becomes 4 geometrical isomers. And then 4 plus 2 stereoisomers, 4 into 2, they are 8 stereoisomers. So I have put a lot of hard work, please go through it, you will understand, nothing to explain. So here is like ZZ, both of them I have kept Z, and then first one. So in this I have put all the OH down, so it is S. Here I put all the OH on top, so this is R. In the R I just kept changing ZZ, EZ, ZE and EE. So ZZ, EZ, this thing and this, right? Okay, so that's it for today's video. Thank you very much.